Hello and welcome everyone to this podcast for cell biology. In this podcast, we're going to talk about energy and cellular reactions. We're going to start by talking about some terms, and in particular, I want to focus on the first and the second laws of thermodynamics. And talk about why these laws are so important in maintaining cellular stability. And then we want to talk about both spontaneous and non-spontaneous reactions. And in particular, how we make these non-spontaneous reactions occur. So how do they occur? So let's go ahead and get started. Now I want to talk about the problems of a living organism. It's not such a problem because at least we get to live, but it's a problem that has to be dealt with. Let's first look at this from the perspective of non-living matter. Things like dead animals or dead trees. They tend to move towards disorder. They break down, they decay. That's what they do. However, living matter may have a tendency to go to disorder, as we'll talk about in a little bit, but they somehow maintain and even gain order. To do this, these living organisms require energy and a source of atoms. It's interesting to think about that the atoms in my body now, most of them weren't around in my body 10 years ago. We constantly need this new source of atoms in order to maintain order. So let's give a working definition of energy. And we'll talk about energy later on in these podcasts and at other points in the semester. But we can think of energy as the capacity or power to do work. So up here, we need energy. We need the capacity or the power to maintain this order. So maintaining the order is the work. Let's define work more formally here. And work is often defined as the measure of energy transfer that occurs when an object is moved, typically by an external force. Let's break down work based on the cell, based on cellular work. And so there's different kinds of work that we can talk about. There's synthetic work. This is work that results in making new molecules. So any of the biosynthetic pathways that we'll talk about or have talked about, so the process of making proteins from amino acids, that would be synthetic work. Mechanical work. This could be the physical change in orientation or position of a cell. Within the cell, we can also think about something called concentration work. We'll talk about this more when we get into the discussions of membranes, but this is moving, or the movement of molecules across a membrane. Against the concentration gradient. So going from a low concentration to a high concentration would be an example of going against the concentration gradient from low too high. We can also think of electrical work in the cell. And this is a great example of this is the movement of ions, so charged atoms, across a membrane against an electrochemical gradient. And then let's define heat. This is energy used to maintain temperature in homeotherms, or warm-blooded animals. And the last one I asked you to know was bioluminescence. And I ran out of room, but I'm going to draw it up here. And this is the capacity of some organisms, some living organisms, to generate light. So now let's move on away from cellular work, and now let's focus on the energy that's used to perform this work. So as we're thinking about energy, let's think about two kinds. Let's think about kinetic energy and potential energy. Kinetic energy is the energy of motion. This is the energy that does the work. This is the energy that moves things. It's the energy that helps move chemicals across a gradient. It's the energy that helps build large molecules. That's kinetic energy. However, not all energy is being used. A lot of times, energy is stored. And stored energy is what we call potential. So potential energy is stored energy. Now, energy could be stored for several reasons. It might be due to its position. Now, your book gives a nice example, I think. It talks about a waterfalls. And so let me try to draw this bit of a mountain here. And we know that water is going to settle up here at the top, but it will begin to fall down this waterfall. The individual water molecules up here at the top have a lot of potential. So that's our potential energy. As this water molecule moves to this edge and drops, that potential energy is converted into kinetic energy, the energy of motion. Now let's think about another example, a more cell biology example. In doing so, let's consider covalent bonds. In order to make this covalent bond here, say a carbon and a hydrogen, they would be sharing these electrons. The energy that is holding this covalent bond together is considered potential energy. So we can say potential energy is held in the chemical bond. As long as this covalent bond is maintained, no energy will be released. But if this covalent bond is broken, that potential energy will be converted into kinetic energy. That kinetic energy that is released from this broken bond can now then be used to do work in the cell. So this is similar to that water in the waterfall. So the water at the very top of the waterfall has potential energy. It's not doing anything yet. Just like this bond, it's not doing anything yet. But as that water falls off the waterfalls, all that energy is converted into kinetic energy. Same thing here. When this bond is broken, that potential energy held in this bond is transferred into kinetic energy. And the kinetic energy will then allow work to occur in the cell. Okay, I'd like to now move into the next area where I want to talk about how cells use energy to maintain order. Okay, let's begin with this first law of thermodynamics. And we can define this law as energy is neither created nor destroyed. However, energy can be converted from one form to another. So let's think of an example here. You can have solar energy coming in from the sun. It can be converted, again, it's not being created or destroyed here, but it can be converted into chemical bond energy. We'll talk about photosynthesis in a little bit, but the energy from the sun can produce, say, a sugar molecule like glucose. And the bonds in this molecule here have a lot of chemical energy associated with them. So this is a pretty good example of how the first law of thermodynamics is fulfilled. As a second example, we can take this chemical bond energy and it can be broken down to form heat energy. Again, we didn't create or destroy any of the energy, we just converted it to a different form. This heat energy can now be used to maintain order in the cell. So this is the first law of thermodynamics. As a consequence of this first law of thermodynamics, the total amount of energy in the universe must always be the same. And this is known as enthalpy, or we often refer to it as simply delta H. So let's take just a little bit more time to talk about enthalpy. As I just said, enthalpy is the total amount of energy in a system, or sometimes we say in the universe. We identify enthalpy as delta H, and delta H can be linked to two terms, exothermic and endothermic. Exothermic is when heat is, where delta H is negative. Now, endothermic is when heat is taken up, in which case delta H is positive. Okay, let's go ahead now and talk about the second law of thermodynamics. This law states that disorder in the universe can only increase. In talking about the second law of thermodynamics, I think it's important to mention entropy. And entropy is the measure of a system's disorder. So another way we could state the second law of thermodynamics is to say that entropy in the universe can only increase. This law has an implication to organisms. If you look at a living organism, such as a flower, or maybe the wings of a butterfly, or the spines of a sea urchin, these are all highly ordered structures. It takes a lot of energy and work to maintain that structure, that order. So the implication to these organisms is this law would suggest that organisms must also increase in disorder. But that's not what we see. We see an increase in order. So how does this not violate this law? Your book gives a pretty good example of this outside of the context of a cell. So let's talk about that as an example. Your book shows a picture of a neat and organized room. And if you've ever seen a neat and organized room, if you've ever been to my office, you might think I've never seen a neat and organized room. But there are times when my office is neat and organized, or at the very least, a little neat and a little organized. But it doesn't really take much for my office to become an unorganized mess. This process of going from neat and organized to a mess is spontaneous. I promise you, I put no energy or effort into creating a messy office. It is spontaneous. This unorganized, messy room here has greater entropy. Let's see, I'll write that here. Greater entropy. It has more disorder. Though you may not believe it, there are times when I put a little bit of energy into cleaning my office. This takes energy. It takes a lot of energy to go from an unorganized, messy room to a neat and organized room. So since we need to add energy to it, it is not spontaneous. I wish it was, but it is not. It is not spontaneous. So having this localized increase in order doesn't violate this second law of thermodynamics, because it's important to point out that it says that there has to be an increase in disorder in the universe. The energy that is used to decrease disorder or to make entropy less is balanced by greater disorder in the universe. So down here I'm going to write local increase in order is offset by greater disorder in the universe. So these local changes here are offset by all the disorder that is in the entire universe, because that is what the law defines, the universe. So this may provide a nice overall example, but this is a cell biology class. So let's think about how increasing order in a cell does not violate this law. So let me draw a cell. And inside this cell, there are lots of molecules. And these molecules exist in a disordered manner. They're moving in different directions, random directions. They are disordered. We know that within a cell, though, we're going to have increased order. So let's draw this cell here. And some of these molecules have created a larger molecule. In the process of this order here, establishing this order, we've generated heat. This extra heat that has been generated causes these other molecules, we'll draw them around here, to become even more disordered, because this heat has raised the temperature, and so maybe they're not only going in random directions, but they're bouncing all over the place because of this heat that has been released by creating some order here. Decreases in entropy because of the order here in this localized region is offset by the overall increase in entropy or disorder in the entire environment. Because of these two interplaying with each other as such, the second law of thermodynamics is not violated in a cell where there is increased order. So how do cell biologists apply the first and second law of thermodynamics? Well, to consider that, let's look at a cell. And in any given cell, there may be thousands of reactions occurring. You may have some reactant A being converted to B. In another reaction, you may have some other reactant C being converted to D. Sometimes these reactions will be spontaneous, and other times they will be non-spontaneous. To determine whether or not a reaction is spontaneous or non-spontaneous, so how are we going to determine whether a reaction is spontaneous or non-spontaneous? We're going to determine this by calculating Gibbs free energy. And Gibbs free energy is shown as delta G. I'm going to write Gibbs free energy underneath it so we don't forget. Okay, delta G is equal to delta H subtract T delta S. If you remember, delta H is the enthalpy of the system, that is the total energy in the system. Delta S, I don't know if I mentioned it before, but delta S is entropy. And then T is temperature. So by considering the total amount of energy in a system, as well as the degree of disorder in that system, and the temperature, we can calculate this value of delta G. So what does this value tell us? If delta G is less than 0, we say the reaction is spontaneous. So if it's a negative number. Now, if that value of delta G is greater than 0, then that reaction would be non-spontaneous. Doesn't mean it can't occur. It just means that energy will have to be supplied to that system. Now, one thing I'm not showing here is what happens if delta G is 0. So let's write that one down here. You might have a reaction that goes from E to F. If delta G is equal to 0, then this reaction, E to F and back to E, is in equilibrium. Okay, I'm going to throw a couple more terms at you while we're looking at this slide. And I'm going to open up the cell here just so we have some more room to work with. A spontaneous reaction, one where the delta G is less than 0, we say that that is energetically favorable. Another way of saying it is to say that it is exergonic. A reaction that is non-spontaneous, where the delta G is greater than 0, we say that it is energetically unfavorable. And we call these reactions endergonic. All right, now I would like to talk about how to make a non-spontaneous reaction spontaneous. Okay, so let's consider this. Let's pretend we have a endergonic reaction. Endergonic reactions require energy in order for them to move forward, in order for them to be spontaneous. Endergonic reactions require energy in order for them to proceed. So for instance, if we had two reactants, say A plus B, and they could be converted into C. But let's say that delta G here is greater than 0. So it's not going to be spontaneous, and the only way to make it work is to throw in energy. And one way to increase the energy is to raise the temperature. By raising the temperature, A and B are more likely to collide with each other to produce C. Another way to increase the energy in this system is to increase the concentration of A and B. If we have more A and B, there's going to be a greater probability that they'll collide with each other to produce C. And the last way here is to couple the endergonic reaction with an exergonic reaction. So for instance, if we had another reaction, let's say down here, reactant D underwent a reaction to produce E plus F, say, and let's say this reaction is delta G less than 0, so it's going to be an exergonic reaction. This exergonic reaction could release enough energy to fuel this reaction, so to speak. The energy from this exergonic reaction can be coupled, is a better way to say, can be coupled to this endergonic reaction. So these are the three ways that you could make a non-spontaneous reaction or an endergonic reaction proceed. Raise the temperature, change the concentration of the reactants, or couple it to a more energetically favorable reaction, an exergonic reaction. And then that energy can be used to drive this reaction. Is reduced, it gains an electron. So that's why they're coupled. When one molecule loses an electron, another molecule gains that electron. And that way they're always coupled. So if you have a hard time distinguishing these two from each other, there are a few acronyms you can remember. When I was young, I remembered it by saying Leo, the lion, says grr. So loses electrons for oxidized, gaining electrons for reduced. Your book uses another one. It's called oil rig. It also works, whatever works for you. Oxidation is loss of electrons for oil, and then reduction is gain of electrons. Sometimes these little tricks help us remember things like this. All right, the last thing I want to talk about is how is it that ATP can be used in a cell to generate energy. You've probably heard in other classes, or if you haven't, I'll tell you now that ATP is considered to be one of the most important energy sources in a cell. But how can it generate so much energy? Well, let's draw ATP. And in looking at its structure, maybe we can see why it has so much potential energy. So it has a ribose sugar on it, just like we'd seen before. And then it has an adenine. And remember, I said when you draw one of the purines, just put 2 rings there. ATP has 3 phosphate groups on it. So it's going to have the phosphorus as well as oxygen surrounding it. These oxygens here each have a negative charge. So ATP has 4 negative charges. And all these negative charges of these phosphates at this end here are being pushed together. And like charges, like these negative charges, tend to want to repel each other. But the structure of ATP forces them together. So this generates considerable energy, or I should say potential energy. Now ATP can be hydrolyzed and forms ADP. I won't draw it all the way out, just ADP. So it has the adenine and the ribose and 2 phosphorus groups here, plus a released phosphate group. This is an exergonic reaction. It's going to release energy. So now, if this reaction occurred in a test tube, this hydrolysis would just be lost as heat. But in a cell, it's not lost as heat. Rather, the energy that's released from this exergonic reaction will be used to make an endergonic reaction possible. So how does this occur? Well, there are several reactions that require a phosphate group to be added to it, to one of the reactants. So let's say we have these two reactants here, this orange circle and purple circle, and the intergonic reaction, if it could occur, would link these two molecules together. However, this being an endergonic reaction, it can't do this unless it gets a little energy. And so it's going to get that through this phosphate group. This phosphate group that's being coupled from this exergonic reaction may, for instance, in our example, bind to one of these molecules, say the orange one. By adding this phosphate group here, it facilitates the interaction between the orange and the purple circle chemicals here, which makes this reaction much more probable because of the energy from this exergonic reaction. Again, what we're looking at here is a coupled reaction. An energetically favorable reaction, the hydrolysis of ATP, is coupled with an energetically unfavorable reaction, and by coupling it, we make an unlikely chemical reaction occur. This process of adding this phosphate group here to make the reaction occur is called phosphorylation. We'll come back to this term frequently throughout the semester. This is a very common way that we activate proteins in order to make certain reactions occur. Okay, that's all I have for this podcast. If you have any questions at all, please make sure you come see me. If not, I'll see you in class. Bye.